In this video, we will talk about the rules of derivatives. The chain rule is what we will talk about in this video. So the chain rule basically says that if you do have a function that is a composite of two functions, p and q, then the derivative of that function is going to be the derivative of the outer function times the derivative of the inner function. Let's see how we're going to apply that rule. It sounds complicated, but it really isn't. So if we have the function 2x plus 7 all squared, then we have a composite of two functions. The outer function is basically something squared, and the inner function is 2x plus 7 in this case. In other words, when we want to find the derivative of a function that is of the form of parentheses raised to the n power, what we will do, let's say this is f of x, we will do the following. We're going to say f prime of x is the derivative of the outer function. So we're going to bring n down times what's inside intact, n minus 1, as if we're using the power rule in this case. But we're not going to stop right there. We're going to multiply that with the derivative of the inner function. So let's say that the inner function is a, then we're going to find a prime and multiply it with the rest of the function after we find the derivative of the outer function. Hopefully that explained this type of expressions. So let's see how we're going to do that in this case. In this case, we have f of x is equal to 2x plus 7 all squared. So we're going to find the derivative of the outer function. The derivative of the outer function is, we bring the 2 down, and then we keep the expression inside the parentheses the same, and then 2 minus 1 is 1. I'm not going to write that down, times, and that's the difference between what we did in the past and what we're doing here. In the past, we find the derivative using the power rule, and then the derivative of x is basically 1. But now the derivative of what's inside the function is something different. What is the derivative of 2x plus 7? We know that the derivative of 2x plus 7 is 2. The derivative of 2x is 2, and the derivative of 7 is 0. So 2 plus 0, and that will be the final answer. Now we're going to simplify that. That will be 4 times 2x plus 7. Distribute. That will be 14x plus 28. And that will be the final answer. So f prime of x is equal to 14x plus 28 in this case. Let's go to a different example. Let's see if we can find the derivative of y is equal to the cube root of x squared plus 4x plus 7. Now, we don't have a rule for the cube root, but we can turn roots into exponential. So we can rewrite this as y equals x squared plus 4x plus 7 all to 1/3. Now notice how this is similar to the previous example. So first we're going to find the derivative of the outer function and then multiply with the derivative of what's inside those parentheses. So y prime is going to be equal to 1/3 comes down times x squared plus 4x plus 7 intact raised to the 1/3 minus 1 times the derivative of what's inside, which is in this case 2x plus 4 plus 0. Now we're going to simplify that. So 1/3 of x squared plus 4x plus 7. 1/3 minus 1 is negative 2 over 3 times 2x plus 4. We have a negative exponent. It goes into the denominator with a positive exponent, and then we can turn it back into a radical form. So this will be 1/3 times 1 over x squared plus 4x plus 7 raised to 2/3 times 2x plus 4. We can multiply 2x plus 4 in the numerator. With the first numerator, we can multiply 3 in the denominator. So that will leave us with 2x plus 4 over 3 times x squared plus 4x plus 7 raised to 2/3. You can leave it like that, but I would like to convert it back to a radical form. You see here is a 3 in the denominator. That indicates we have a radical with index 3. And the 2 will remain there over these parentheses. So we're going to have 2x plus 4 over 3 outside, and then there is a radical with index 3. So it is the third root or the cube root of x squared plus 4x plus 7, but this is raised to the second power. Remember, the 2 remains, so that will be the final answer, and that is the derivative of this function using the chain rule. Here is an application example. Like the rest of the world, the increase in the number of internet users has slowed in Latin America during the second decade of 21st century. Using data from 2013 and projected to 2020, the number of internet users in millions in Latin America can be modeled by y equals 201x to the 0.3, with x equal to the number of years after 2010. Name the function that models the rate of change in the number of internet users in Latin America. Find the function from part A. Predict the rate of change in the number of internet users in Latin America in 2025. The solution: we know that the rate of change in the number of internet users in Latin America is modeled by the derivative. So we're going to find the derivative of that function. And to do that, we're going to take the constant 201 outside, drop the exponent down and subtract 1 from the exponent using the power rule, just like before. The final answer is going to be 60.3x to the negative 0.7, and that is the rate of change in the number of internet users in Latin America. To find the third part is to predict the rate of change in the number of internet users in Latin America in 2025. We're going to find how many years between 2010 and 2025. So we find the answer to be 15, and then if you plug that into the derivative that we find in part B, that will give you the rate of change, or that will give you the prediction of the number of internet users in Latin America in the year 2025. And there is a typo in this, and I will fix it. This model predicts that the number of internet users in Latin America will increase by 9.06 million between 2010 and 2026. So let's try this. The total personal income in the United States has risen steadily over the past decade from 4.9 trillion US dollars in 1990 to 15.3 trillion US dollars in 2015. This personal income, which is we're going to call it the function I, in billions of dollars from 1960 and projected to 2024, can be modeled by I of t is equal to 6.12 t squared minus 49.7 t plus 620, where t is the number of years after 1960. For 2020, find the model's prediction for the total U.S. personal income, the rate of change of the total U.S. personal income. So I'll give you a hint. The total U.S. personal income for 2020 is basically this ready model that is provided. And given that T represents the years since 1960, we're going to count how many years are there from 1960 to 2020. After you find that number, you're going to plug the answer in the original function or the original model that is provided. Then to find the rate of change of the total U.S. personal income, you're going to find the derivative of I of t using the derivative rules that we learned before. If you're confused by t, replace t by x and you will be good to go. And then you're going to plug the number of years from 1960 to 2020. You're going to count into the derivative of I of t. You're going to plug it into I prime of t and find the answer to the second part of the question. So let's see that in the next slide. You can pause and answer and then compare your answers to my answers. So the first question is, we're going to compute how many years from 1960 to 2020, that is 60 years. And to figure out the personal income in 2020, we're going to plug 60 in the original model or the original function provided. The answer is going to be $19,670 billion. That is the predicted personal income in dollars. The second part is to find the rate of change. To find the rate of change, we're going to find the derivative of the provided model or the provided function, which is I prime of t. I prime of t is equal to 12.24t minus 49.7. For the year of 2020, we're going, since t represents the year since 1960, then we're going to find how many years from 1960 to 2020, which is 60 in this case. And to find the rate of change of the total US personal income, we're going to plug the 60 in the derivative of the function of personal income function, which is provided and we found previously, namely right here. So you're going to plug 60 and the final answer is going to be the expected or the predicted rate of change in the total US personal income in 2020 is $684.7 billion per year. Let's look at the second example. We're going to discuss an application of the derivatives, which is finding horizontal tangents. Find all of the points on the graph of f of x that is equal to x cubed plus 3x squared minus 45x plus 4, where the tangent line is horizontal. So to understand that, it is important to understand that the slope of a tangent line of a function f is the derivative of the function f. That is the first thing. The second hint is the horizontal line has a slope that is equal to 0. Those two ideas that we're going to use to find those horizontal tangents. So to find all the points on the graph f of x where the tangent line is horizontal, we're going to find the derivative of the function. So we're going to find f prime of x, which is equal to 3x squared plus 6x minus 45. Then we're going to find all of the points where the slope is equal to 0, and this is basically the slope of the tangent line. Wherever the slope is equal to 0, we're going to have a horizontal tangent. So we're going to make this is equal to 0 and we're going to solve it. So we're going to take the 3 out as a common factor and we're going to have x squared plus 2x minus 15 is equal to 0. Now we're going to divide both sides by 3 and we'll end up with x squared plus 2x minus 15 equals to 0. This is basically a quadratic equation that we can solve. So we have x and x, we need two numbers. Their product is negative 15 and their sum is positive 2. Those two numbers are positive 5 and minus 3. Now we're going to solve. So we're going to say either x minus 3 is equal to 0. That will give us x is equal to 3. If you forgot how to solve quadratic equations, please go back and review the strategies of solving quadratic equations. You can also use Desmos to solve quadratic equations. You have to look that up. Or x plus 5 is equal to 0, and that will give us x is equal to negative 5. So the first thing is when x is equal to 3, what is the point at which the first horizontal tangent is going to be? And to find that point, we're going to plug x is equal to 3 in the original function to find the y coordinate. To do that, the answer is going to be 3, and you plug 3 here, so you're going to get 3 cubed plus 3 times 3 squared minus 45 times 3 plus 4, and the answer is going to be negative 77. For the second part, you're going to do the same. So when x is equal to negative 5, what is the value of the y coordinate? And you're going to plug negative 5 in this function. You're going to get negative 5 all cubed plus 3 times negative 5 squared minus 45 times negative 5 plus 4. And the final answer is going to be 179. So the first point at which we're going to have a horizontal tangent is 3 and negative 77. The second point where we're going to have another horizontal tangent is negative 5 and 179. The marginal revenue, that is another application of the derivatives. The definition of the marginal revenue is as follows. If you are given the revenue function R of X, then the marginal revenue, R prime of X, is used to estimate the change in revenue caused by the sale of one additional unit. Let's look at an example. Suppose that a manufacturer of a product knows that because of the demand of this product, his revenue is given by R of X is equal to 1500X minus 0.02X squared, where X is between 0 and 1000. That means he can only produce 0 to 1000 units, where X is the number of units sold and R of X is in dollars. We want to find the marginal revenue at X is equal to 500. We want to find the change in revenue caused by the increase in sales from 500 to 501 units, and let's compare the two. So to find the margin revenue, we know that the margin revenue is represented by the derivative of the revenue function, meaning we're going to find R prime of X, which is in this case 1500 minus 0.04X. So that to find the margin revenue at X is equal to 500, we're going to plug 500 in the margin revenue function that we found. And the answer is going to be 1,480. This means that the approximate revenue from selling one unit after 500 units will be $1,480. Let's look at the second part. To find the second part, we're going to use the traditional method of finding the marginal revenue. That means we will predict the revenue at X is equal to 500, and then we're going to find the revenue when X is equal to 501, and from there we're going to see how much revenue is made for that one unit extra after the 500. The revenue at X is equal to 500, we're going to plug the 500 in the original function given, the revenue function, and we're going to get $745,000. That is the revenue from selling 500 units. And then the revenue from selling 501 units is we're going to plug 501 into the revenue function that is given. We will get 746,479.98 cents. And to find the marginal revenue, we're going to subtract the numbers to figure out how much revenue is made from the extra one unit, which is basically the marginal revenue. So to do that, you're going to subtract the two numbers and you're going to get $1,479.98 with a difference of 2 cents between the predicted way of finding the marginal revenue and the actual way of finding the marginal revenue, which leaves us with the idea that if we find the derivative of the revenue function, we will get the marginal revenue easier that way. Let's try this one. So pause here and try to do it on your own. Suppose that a wholesaler expects that his monthly revenue in dollars for an electronic game will be R of X is equal to 100X minus 0.1X squared, where X is between 0 and 800, and X represents the number of units sold. Find his marginal revenue and interpret it when the quantity sold is 300 or 600. So to do that, I'm going to give you some hints. To find the marginal revenue, then you're going to find R prime of X, which is equal to 100 minus 0.2X. Now, when X is equal to 300, you're going to find R prime of 300, which is 100 minus 0.2 times 300. And then you're going to find the answer. The number you're going to get here is the revenue expected from selling the one extra unit after 300 units have been sold already. So that means the revenue from the 301st unit is going to be represented by the marginal revenue function. To do that for 600, it's exactly the same process. So you're going to find the marginal revenue at 600 units, which is 100 minus 0.2 times 600. And then the answer here is going to represent the revenue expected from selling the 601st units. It's not the revenue from 601 units. It's the revenue expected from selling one extra unit after selling 600 units from that product. Notice how my numbers are between 0 and 800. I can't predict anything above 800 because this model does not represent that. So if I tell you find when x is equal to 1000, you're going to tell me, well, I don't have a model for that. My model expands from 0 to 800 and I can't predict more than that. This is how you're going to work on this type of questions. Let's try another one. Suppose that the revenue function for a flash drive is given by R of x is equal to 10x minus 100x over 3x plus 5, where x is the number of flash drives sold per day and R is in dollars. We want to find the marginal revenue function, which is find the derivative of R of x. So to find the derivative of R of x, you're going to say the derivative of 10x is 10 minus, and here is where things get interesting. So we know that 100x over 3x plus 5 is a quotient function. Let me remind you of the derivative of quotient functions. The derivative of any quotient function is the denominator times the derivative of the numerator minus the numerator times the derivative of denominator over denominator square. So in this case, f is equal to 100x and g is equal to 3x plus 5. So if I find f prime, then the answer is going to be 100. If I find g prime, the answer is going to be 3. Now I'm going to replace, so g is the denominator, 3x plus 5, and since it has addition in the middle, I'm going to put it between parentheses, times f prime, which is 100, minus from the formula right here, f, which is 100x times the derivative of g, which is 3, over the denominator square, which is 3x plus 5 all squared. So this will be 10 minus, then you're going to multiply 100 inside. I'm going to put parentheses again because I have the minus. I have to distribute that, so I have to keep the parentheses until it's safe to remove. This is 300x plus 500 minus 300x over 3x plus 5 all squared. The 300 is going to cancel with 300x and I will end up with only 500 in the numerator. So r prime of x is equal to 10 minus 500 over 3x plus 5 all squared, and that is the marginal revenue function. Now we're going to find the marginal revenue function when x is equal to 15. You're going to remove x's and replace that with 15 and find the answer. The interpretation is the prediction of selling the 16th flash drive is going to be whatever the answer to r prime of 15 is. Here is a quick calculator note. Most graphing calculators have a feature called numerical derivative that can approximate the derivative of a function at a point. To find the numerical derivative of f of x at x is equal to c using a graphing calculator, choose the math menu and select 8, which is n deriv. Next, enter the function and then comma x, comma the value c. So the display will show n deriv f of x, comma c, then press enter and the numerical derivative will appear. This can be handy for some of you, especially those who have TI-84. The process is a little bit different for TI-83, but you can figure that out on your own. It could be handy sometimes. It's not always the best option. I prefer to do it manually, but it could be a good option for some of you. So you can play with the feature and see if you can actually use it and if it's going to help you. here is an example on how to do that. If you want to find the numerical derivative for r of x, which is 1500x minus 0.02x squared with respect to x at x is equal to 500, then the derivative, to find that using the calculator, you're going to use the following steps. You're going to go to the math menu and select 8 and then enter 1500x minus 0.02x squared, which is the function, and then comma, the variable you're using, which is x, comma, the value, which is 500, and that will give you 1,480, which is we found in the previous examples. So try and play around with this feature and see if it's going to be helpful for you. Demand. Demand is another application for derivatives, and here is an example. The demand of x 100 units of product is given by x is equal to 98, 2 times p plus 1 all raised to the negative 1/2 minus 1. P is the price per unit in dollars. We want to find the rate of change of the demand with respect to the price when x is equal to 24. To do that, we're going to find the rate of change of demand, which is the derivative of the function given. And to find the derivative of the function given, you're going to use the chain rule in this case. First of all, we're going to take 98 outside because it is a constant, so we're going to leave it outside. Then you're going to bring the power of the parentheses or the exponent of the parentheses down, which is negative 1/2, and subtract 1 from the exponent. And then you're going to multiply with the derivative of the inner function, which is 2p plus 1. With respect to p, in this case, the answer is going to be 2. Then you're going to simplify. Negative 1/2 times 98 times 2 is negative 98. Times 2p plus 1 raised to the negative 3/2. Now we're going to find the rate of change in demand when p is equal to 24. To do that, we're going to plug p into the resulting function. The final answer is going to be negative 2/7. To interpret that, this basically means that when the price is $24 per unit, when the price is $24 per unit, the demand is changing at a rate of negative 2/700 units per dollar. If you do have any questions about any of these applications, please let me know. I apologize for the background noise of my kids playing around. I hope that my videos were clear enough, and I apologize for the background noises caused by my kids, specifically my 3-year-old, and I will see you in a different video.